Okay, welcome to Dynamic Memory in C. For any of you who have had this in your introduction to C course, this is going to be a refresher. I know a lot of introduction to C courses don't cover this, so consider this your introduction. This is something that we're going to make a lot of use of in the rest of the data structures courses, so just be along for the ride. Hope you enjoy it. I'm Brian, by the way, so let's get started. Okay, C is a very old language. It's a very simple language. It was originally written to port Unix, the operating system, in, and it's very oriented towards very basic memory management functions. So, four basic functions in C: malloc, free, calloc, and realloc. So, just at a high level, what do these things do? Malloc is the very basic memory allocation function, returns a pointer to allocated memory on success and null on failure. The memory that's returned, if it is returned, is not guaranteed to be cleared to zero. Free releases previously allocated memory from one of the other memory functions. Nothing is returned. You can assume that this always succeeds the first time you call it on a pointer that was returned by something else. Calloc allocates memory and clears all the bytes to zero. So if you do need to make sure that the memory that you're getting back is cleared to zero, then use this. Do not use malloc. The pointer it returns is guaranteed to be completely cleared to zero and null on failure. All right, realloc changes the size of memory that was previously allocated with malloc or calloc. It returns a pointer to allocated memory which may or may not be the same as what you passed in on success. Okay, and just like all the other memory functions, it returns null if the reallocation was not successful. All right, let's talk about these more in detail. Malloc is short for memory allocate. This is the fastest of the memory management functions. It just finds the first thing that satisfies the request and returns it. It is used when you don't care about the contents of the memory that's returned. Okay, so this means that you're not going to check any of the contents of the memory that was returned because it's not guaranteed to be anything in particular, and you're going to be doing all the initialization yourself. So a lot of times we want to do that in our own libraries. Um, Number of bytes is passed into malloc. Okay, so if you want something that is more than 1 byte in size, you have to use the right number of bytes. You can use C's size of operator to do this. You may or may not have encountered this in your introduction to C course. So for example, if I want to allocate memory that's going to hold an int, I can use malloc size of int. And because size of is an operator, this is evaluated at compile time, and the thing that I put in the parentheses can be either a type or a variable. Okay. And if for some reason you do this wrong, the compilation will fail. Your program will not even compile if you screw this up somehow. So this is kind of a good thing that size of is an operator and not a function. The common way that you're going to see memory allocated like this is to declare an array of things. And we're going to be doing this during some of our examples as we go through our data structures courses. So for example, if I wanted to declare an array of 42 ints, then I need 42 times the size of an int in order to make sure that I have enough memory to hold all 42 ints in my array. So you see here 42 times the size of int. So it's the number of things I want in my array times the size of each element in the array that I need to pass into malloc, because malloc only operates on a total number of bytes. All right, when do we use free? We use free when we are completely done with a piece of memory. It doesn't matter which of the other three memory allocation functions were used to originally allocate the memory, or if memory was previously reallocated. Doesn't matter. They're all valid to pass into free. Make sure that you don't attempt to use a pointer once it's been freed. Okay, if you attempt to use a pointer after it's been freed, it will probably make your program crash, and if it doesn't, it should. And the basic reason is that once it's been freed, the memory allocator doesn't guarantee that it won't reuse that space. So after you free it, if you try to use it, it may contain something completely random from your program's perspective. Also, make sure you don't attempt to free a piece of memory that's already been freed once. This will also probably make your program crash. The reason is the second time you pass in the same pointer into free, the function is going to go look up the information associated with that piece of memory, and it's going to fail to find it because it's already freed it once. And that failure to find it usually results in a fault in your program and crashes it. Always set your pointer to null after you free it. I recommend writing both the free and the null on the same line so that you don't accidentally forget to set it to null. This is just good habit to get into. This is the only time you will ever see me recommend writing two C statements on the same line. But it's just good to do this. You know, it makes it explicit. It gets you in the habit of doing it so you don't accidentally forget and, use a pointer that you've freed and not set to null. It is totally fine to free a null pointer. It just doesn't do anything. So if you pass a null pointer into free, nothing happens. So this is another good reason why setting your pointer to null is good practice, because then later if you call free on the same variable and it's been set to null, no harm. It just does nothing. This also means that you don't need to check if a pointer is null before freeing it. In fact, don't check if a pointer is null before freeing it, because free does that too. So putting a check for null before you call free just does extra work that achieves nothing, because free is already going to do that for you. Um, One other note on this, the reason that you set the pointer to null after you free it is so that you can check to see whether or not that memory is allocated. If you guarantee in your code that you always set a freed pointer to null, then it's always going to be safe to check for whether or not the pointer is null to validate whether or not memory is allocated to that pointer. So get in the habit of this. It's just going to make your program safer, easier to maintain. All right, when do we use calloc? Calloc is short for clear memory allocate. This is what you use when you need to guarantee that everything that comes back is going to be set to 0, or when you're going to be initializing it to 0 anyway. Okay. This is really important for some libraries. Generally, if the memory that you allocate is going to be passed to a library you didn't write or a function you didn't write, you should use calloc, because you don't know what that other library's initialization function is going to do. Some of them, especially I run into this in some Unix libraries, do check the memory that's passed in to see if it's already 0. And if it's not, you can run into all kinds of strange behavior, usually behavior that crashes your program. So it's just good practice if you're going to be passing in the memory you allocate into an initialization function in a different library, use calloc when you allocate the memory. Using calloc is usually slower than using malloc because of the extra work done to guarantee that all the memory is set to 0, but it's usually faster to set it to use calloc than it is to set it to 0 yourself. Some operating systems have some special functionality built into them so that when calloc is called by your program, it does some fast operations under the covers to make sure that what is returned to you is all 0. And those mechanisms are usually faster than literally byte by byte setting it to 0 within your program. So if you know that you're going to be setting all the bytes to 0 anyway, just go ahead and use calloc and don't try to use malloc and then set it to 0 yourself. All right, calloc takes two parameters. Okay, the first one is the number of elements. The second one is the size of each element. This is historical reasons that caused this. This is just the way it was written initially, and C is now a standardized language, and so this is the way it will always be. So don't worry too much about the fact that it's got two parameters. Just always use one for the first parameter. Use the number of bytes that you want as the second parameter, and just keep your life simple. There's no reason to ever use anything other than one for the first parameter. Just know that this is just the way Cialic is written. This is the way it's always been done. And so we just use one as the first parameter and don't worry about it. All right, realloc, short for reallocate. Usually we use this when we need to make a piece of memory larger. We can use it to make a piece of memory smaller, and there will be things that we will do in some of our data structures lessons where we do this just so you have the experience of doing it. Um, but usually, if you're making a piece of memory smaller, that means you're going from small to big, back and forth. And reallocating memory is slow for the operating system to do. So if you're in one of those situations where you're going back and forth between small and large, it's usually best to just leave it alone when you're making it smaller and just focus on making it bigger when you need to. The parameters to realloc are the pointer that you want to reallocate and the desired new size, not the number of bytes to be added. Okay, so the size parameter is the total new size that you want it to be. Okay, so original size plus or minus the size amount that you want to change. Realloc may have to allocate a new block of memory in order to satisfy the size that you passed in. And if it does this, it's going to copy over the contents of the old memory to the new memory. So you're always guaranteed that whatever realloc returns to you is going to contain the contents of the original memory that you passed in. Okay. Realloc returns a pointer to the memory of the new size that you requested. And that may or may not be the original pointer that you passed in. Never assign the return value to the same value you passed in. Use a separate value for this and then check. We'll get into the reasons for this in a second, but just bear in mind, never ever assign the value that's returned from realloc back to the pointer that you passed in. It will cause problems. Okay, malloc, calloc, and realloc can all fail. Uh, Usually that happens when the operating system doesn't have enough memory to grant you the size that you requested. And this does happen. I have seen this happen in the real world. If it does fail, if one of these functions fails, they will return null. So always check the return value of one of these functions to make sure that it's not null before continuing, and handle any failure gracefully. It is always fine to tell the caller of your function that you weren't able to do what you needed to do, but it is not fine to make their program crash. Um, so, always make sure you handle the null case. If you don't check for null and memory allocation fails, and then you go on and continue to use the memory assuming that it succeeded, you will crash. Anytime you try to use a null pointer, you are guaranteed to crash. So always make sure you check. All right, let's talk about the situation I mentioned a second ago with realloc. Okay, again, never ever assign the return value of realloc back to the same pointer that you just passed in. Realloc does not do anything with the pointer you pass in if the reallocation fails. Okay, so if you reassign the return value of realloc back to the same pointer variable and realloc fails, the new value of that pointer is going to be null. And because realloc didn't do anything with the pointer that you passed in, now you have no way of knowing what that original address was, and you can't pass it to free. You cannot free that memory any longer. Okay, so that is what's called a memory leak. Anytime you lose the context, the address of a pointer variable and are no longer able to free the memory that was associated with it, that's called a memory leak. Okay, what is a memory leak? Okay, as I just mentioned, happens anytime you have uh, lost the pointer to the memory before that memory is freed. Okay, we just talked about one way to do this. Another way to do this is if you forget to free the memory that you allocated within a function before the function exits, because the pointer in that function will disappear when the function exits, and you won't know what it was and won't have any way to free it. Okay. Another way this can happen is if you had a pointer that already pointed to memory and you assign the return value of another memory allocation function to that same pointer before you freed it. So the pointer after that is going to hold the value of the new block of memory, and you will have forgotten the address of the old block of memory, and it'll be forever lost. Have no way of recovering it. Over time, if you have memory leaks, even small memory leaks, even a memory leak of 1 byte, over time will cause your program to consume larger and larger amounts of RAM. If your program consumes enough memory, it will start interfering with the operation of other programs on the system. Because what's going to happen is that the operating system will not be able to grant other programs the memory that they are requesting because your program is consuming so much of it. And usually at that point, the operating system is forced to kill your program in order to make enough RAM available for everything else to run. The operating system tries to guarantee fair usage of all the resources, and RAM is considered a resource. So if it detects that your program is consuming all of the available memory, then it will kill yours because yours is not being fair to the rest of the programs in the system. All right, let's talk about some best practices around uh, allocating and deallocating memory. So when you write a line of code that allocates memory, go ahead and immediately write the line of code that will free it. Okay, so just write one after the other. I'm going to allocate and then I'm going to free. And then put the logic of using the memory in between those two lines. We're using text editors. We can add and delete to our heart's content. So just add the logic between those two lines. That way you're guaranteed that the free line is already there. You don't have to worry about accidentally forgetting to free a piece of memory. There is an exception to this. If the purpose of your function is to create and initialize a block of memory that you are returning to the caller, then obviously you don't want to free it before you exit, right? So in our data structures, we're going to write some functions that create and initialize a data structure using these functions, and we're going to return the pointer to the memory that we initialize back to whoever called our initialization function. So situations like that, you don't want to free it right after you allocate it, because that is going to be used by the caller of your function. All right, there's different ways to structure functions. Some people say that you should only have a single return statement from a function. And if you write code like that, great. That means you only have to worry about a single free call in your function if you're going to free the memory before you exit. Other people, though, look at that and say that that can be kind of messy to write under some circumstances. And so they'll write code in such a way that um, the function will exit early if it doesn't make sense to continue the operation of the function from that point forward. So people who write code like that have multiple return statements in their code. I'm not going to judge one way or the other, but if you do write code that has multiple return statements, you'll need to make sure that you free the memory that you allocate before each one of those return statements. Free memory in the reverse order that the pointers were allocated. Okay, this is pretty common practice. This helps write some error handling code. The Linux kernel, for example, this is the way everything is written in the Linux kernel. The pointers are freed in reverse order that they were allocated during the error handling of the kernel code. So a lot of stuff is written like this in C. Just get into the habit. You're going to see it a lot. It's good to get familiar with the structure of doing that. All right, let's talk about an example. So here we're going to test random numbers by plotting a histogram. This is just an example. The plot histogram function doesn't really exist, but let's just look at how we would uh, do this. So we're going to declare that we're going to have 64K or 65,536 numbers. So our number of numbers is equal to that. We're going to allocate an array that is large enough to hold that number of integers, right? Because our histogram is going to count the frequency of the numbers as we go through here. And because we're counting a frequency, we want all the values to start at 0. So again, anytime you know that you're going to be setting all the values to 0 anyway, go ahead and use calloc. So that's what we're going to do here. We're going to use calloc, one element of num numbers times size of int, and that will give us an array that is num numbers, or 65,536 elements in size, integers in size. All right, then we've just got a simple for loop that's going to run a million times. We're going to use our rand function that you've probably seen in your introductory course, and each integer within the histogram, we're going to go through, we're going to increment the count at that number every time we go through this, and then we're going to plot our histogram. At the end of that, we're going to free our memory and set our pointer to null. Now, notice here, this is a void function, and this is the last statement in this function, so nothing else happens after this, and yet I've still set my histogram pointer to null here. Do it. Even though you don't need to, get in the habit of doing this. Just make it a point to always have your pointer set to null right after you do your free. It's just a good habit to get into. Okay, here's an exercise for you. So write a program that allocates an array of 26 characters, and then use a for loop to initialize the elements to lowercase letters A through Z. Okay. Remember, in C, characters are just numbers. So if your index variable is between 0 and 25, you can write something like my letters index variable equals, the character A plus your index variable. Okay. And then write a second for loop to print out all the letters in the array. Then go on to resize the array to hold the capital letters as well, and write another for loop that sets the elements of the array beyond the first alphabet to the capital letters A through Z. And then you can use another for loop after that to print out the full array. So then your last for loop will print out lowercase a through z followed by uppercase a through z. And then free the array and exit the program. Okay, that's it. I do recommend that you go through the exercise, but I will post the link to the GitHub directory where the code and these slides are located. So you can check your work after you've done the exercise to look back and see my way of doing it. And your code doesn't have to necessarily be exactly the same, but you can use it as a reference and you can see how close you got, or if you have any problems, you can look at that to see how you might move on beyond beyond what you're stuck with. So good luck. Do some exercises, play around with it, and I will see you in our next video, which is going to be the first video about our data structures.